Here we have a circle, and there's a point A over here and a point B over here, and they define an arc. Well, one of the arcs they define is this one, the one we're interested in, and we're going to talk about some angles. This angle here, which is subtended at the center and stands on the arc. I think of subtends means where the pointy bit is. So this angle, the pointy bit's at the center and it stands on the arc, and this angle here, the pointy bit's on the circumference, so it's subtended at circumference and it stands on the same arc. And what we're going to show today is that no matter where you put point C, that it is always 60 degrees, which is half of the angle in the middle. The angle, of course, isn't always 60 degrees. It depends on where you've got A and B. So if you move this point here, say, round, and you try and make it into 100 degrees, then this one will be 50 degrees, half of it, and again, it doesn't matter where you put it. It's always the same. So if you put it in here, then the arc changes. So the arc becomes this red arc around here, and this angle here, 60 degrees, is twice this angle of 130 degrees, no matter where you put this angle here. So let's put it back the way it was, clicking that button, and we are going to do the proof, or we'll demonstrate the proof. One copy of the red angle needs 2 copies of the green angle to be exactly the same. So that's what we're going to demonstrate. So to do the proof, you use triangles, you draw a line, you make up a point called M, which is down here somewhere, but it's the point about M is that it's on a line that starts with C and goes through O. And so you just dot that in, and so now you've got 2 triangles. And the whole proof is based around the exterior angles of an isosceles triangle. So we're going to have a look at that first. So basically that's saying that if you add this blue angle and this red angle together, you get 180 degrees because they are sitting on this straight line. So that's what's written down there. And then you do some algebra and you get this angle by itself on the left. Subtract AOC. And then you look at the other side, the same thing occurs. And then you look at this triangle here, you say that angle plus that angle plus that angle add up to 180 because they are in a triangle. And then you do some algebra on that, and you see that basically if that angle and that angle and that angle add up to 180, and that angle and that angle add up to 180, and this angle is the same in both cases, then this angle must be the same as this angle plus this angle. So you do algebra, substitute that for that, then you get this, that this angle is the same as that angle plus that angle, and then going further we can say that that's a radius and this is a radius, so that these angles are the same. So instead of writing OAC, you can say, well, those angles are the same, so you can write OAM is OCA plus OCA, or AOM is 2OCA, and that holds on the other side as well. And you can demonstrate that by saying that 2 lots of those green angles is the same as that one, and it doesn't matter where you stick that. These angles will add up nicely. You can put it over here. Still, 2 green angles is a blue angle, and you go into the other side. 2 green angles is the same as the blue angle. And that's the exterior angle of the triangle. Right, so now we're going to go and put the thing back the way it was, and we're going to go through the proof. So we've drawn our line, and then we have looked around for some radii, their radii, and if you look on the other side, their radii. And then you say that that angle is the same as that angle because they're opposite radii, and that's something that you know about triangles. And if you look on the other side, same thing. Then you say that that angle is the same as that angle plus that angle, which is the old exterior angles thing again. And then you can say that that angle is worth 2 of those angles because that angle is the same as that angle. And then you look at the diagram and you can see that the big red angle is the same as AOM plus BOM. That's just from looking at the diagram. And then you can say that AOM is the same as 2 lots of OCA, and on the other side, BOM is the same as 2 lots of OCB, which is what we found out earlier. And then you can do some algebra, and then you can say that OCA, the little blue angle, plus the other bigger blue angle is the same size as the green angle, and that is basically what we set out to prove, that this angle is always, the 2 lots of this angle is the same as this angle, or this angle, so this angle is twice as big as this angle, or this angle is half of that angle. And you can muck around with it and do that. We'll move this around here. Still, all the maths holds out, and that is the proof.